All right, let's get going. We are in week 11. Dun, dun, dun. More people might crawl in, but let's get started so that we are on time. So we've talked about databases the last couple of weeks, and today we're going to enter into something different, but we will still keep talking about databases every single week because we have to change our schemas quite a bit. All right. And today there will be actually quite a lot of change in schema as well. So let's see what's going to in our database schema. I mean, so let's see what's going to happen. All right. Um, Before I get started, any questions about what we've done so far in previous weeks? Any issues or problems? No? Yeah, Shelly. Okay, so you're having a problem with serializing, with serializing records because of yeah. I saw Yenyu's GitHub repo, but I didn't get a chance to clone it and actually play with it. Is anybody else having that problem with like encrypted columns? Yes, no, not really. So these two teams are having the same problem. Okay. If I have time at the end of today, we can try to debug it together. Otherwise, I'll have to do it maybe virtually with you after class. Is there anything specific about the problem you want to mention? Because I haven't quite gotten to the root of what the problem is yet. Okay, then we'll talk about it later. Okay, I would like to try to get a chance to see how to fix that. All right. Okay. Um, so so let's get going and let's see if we can make some time at the end to see that. Um, so today we're going to talk about user accounts. That's going to be today's topic. So far I've asked you, please, please, please resist from creating users yet. And but some of you, I think maybe one team had to actually do it because that's maybe your major entity, right? Okay, well, for the rest of you and for you, I'll kind of give my perspective of these accounts and things and how they work. All right, okay. So let's start. So starting from today, we're going to be talking a lot about trust. I have trust issues, basically. Okay. So I want to talk about trust, and we're going to be talking about this for many weeks. In fact, for most of the rest of the semester, because as you're going to find out, what we call in IT security is really trying to formalize the trust that exists between people already, and the trust that we have in our users, the lack of trust we have in people who are trying to do something bad. All right. So when we talk about IT security in this class, we're essentially trying to create systems that can formalize, that can collect evidence of trust from users, that can verify that who we trust, that can transfer our trust to other machines, and that can store trust. Okay, so let's start first of all with we have this big system, and I've kind of tried to draw this out. Like, this is what we have today. It'll get bigger before the semester is over, but this is kind of the overall system architecture that we have today. Okay, and essentially, what this system is asking is for every single component, the browser, the application, the API, the database, it's asking for each of these to trust that what they are doing and they're being asked to do is correct. Okay. If the database, if the API is told, well, we don't really code the database, we code the API. If the API is told, wipe out the database, should it do it? Does it trust the person making this request? If the application is told, hey, you need to get this record with sensitive information from the database, please ask the API. Should the application trust this request? Should the API trust the application when it makes this request? In fact, how does the API even know that the web application is the one making the request? How does it know somebody didn't just like find this API somewhere and like just make this request? All right. So how do all these different components trust the orders that they're being given to do, the requests they're being given to asked to fulfill? And where does this trust come from even? All right. So we're going to start that discussion today in a small way, and we'll get into that more in later weeks when we get into topics of authorization. Okay. So first of all, for this week, we are not going to ask the difficult question of how do these components trust each other. Okay, we're not going to ask that question today. We're going to come back to that in a later week. But assuming that we're asked to do something, where do we get our trust from? Why do we believe that what we're being told to do is the correct thing to do? It's not something malicious, it's not something dangerous, all right? The source of our trust in our entire system is her. I don't know her name, but it's her. Okay, it's the user, what we usually call the user. We Alice, yes, thank you. No, not Eve, not Edgar. Okay, it's Alice. Sure, I should write Alice here. Fantastic. It's Alice. That's the person we trust, and in fact, if we can trust that this is Alice and this is really Alice, we are willing to do whatever she tells us to do. That's within the bounds of what she is allowed to do. Okay. So today's problem is, how do we know this is Alice? Who is this person who's talking to us? All right. And we're going to start with that topic today. So we have to kind of validate that we are indeed talking to Alice. All right. Okay. And when Alice sends a request, we're going to eventually, not this week, it's going to be the browser who's going to talk to Alice. All right. And the rest of our system, the application and the API, never really talks to Alice. This is kind of a strange thing, right? We never talk to Alice. The API, in fact, is a customer of the web application. Not a customer, excuse me, is serving the web application, right? And the web application is serving the browser. Only the browser ever talks to Alice. The rest of these folks have to just believe that it's Alice, right? Okay. Um, And in particular, the browser is the one who collects evidence from Alice to say, yeah, this is Alice and these are Alice's genuine requests. The web application, which we have not yet written, will eventually simply transfer that evidence. Like the application doesn't, is kind of right in the middle. It just transfers that evidence. And it's the API that has to verify eventually, yeah, this is Alice. This is who I believe is Alice. And it has to store the evidence that it needs to trust Alice in a database. Okay. And then later on, when Alice makes a request, it's the API who has to recollect all the evidence of who is Alice and how do we verify Alice, and and actually make the decision that this is indeed Alice we're talking to. All right. So this is going to be a long process, and we're going to talk about this for several weeks. Okay. But we'll start today with by asking what kind of evidence should the user give us to believe to make us believe it's them, and how do we safely store this evidence in a database? So we'll start at the two ends of this problem. Okay. Um, any questions before I move on? I know that's a little bit abstract, but the essential idea is we need to learn to trust people. Right? It's like, as every good psychiatrist will tell you. Okay. So what do we need to trust people? What is it that we need? When a user comes to us and says, hey, delete all my records or give me all my records, what do they need to present to us for us to believe them? This is an authentication problem. We're not quite going to do authentication today, but we're going to start collecting the things that we need to do authentication. All right. What we're going to ask from people, from users, is credentials. So when we say credentials, usually you think of username, password. These are what we typically call credentials. Okay. The word credentials may be a little bit unusual if you're not a native English speaker. It's not necessarily a word you use every day. But the heart of it is this root word cred, which means to believe. All right. So a lot of words in English have this root Credible means somebody who is believable, who you can believe. Okay. Credibility is, that you means that some information is believable, how believable something is. Incredible means it's not believable. It's barely believable, right? Credit, right? Like you go to a bank, you get credit. Credit simply means we believe we can give you things. We believe we can engage with you in things. Credit worthy, credo, credulous, incredulous, all of these words have this word cred in them. Okay. So, and credentials usually means, and I had to go to a dictionary for this, some kind of qualification or quality or aspect or something about somebody that makes them suitable, um, to indicate that they're suitable for whatever they need to be doing. All right. In our case, the credentials we are going to be asking from people is going to be information that we need to know who they are later on. Okay, so today we're not doing authentication. We're not going to try to verify this is the right person. Today we're simply assuming that you're talking to the right person. Let's assume that for a second. All right. What is the evidence we need to collect from them so that later on, when they come back to us, we have enough information, or we can ask them for the particular information again, and they can verify who they are. Okay. So three things typically go into user credentials. All right. Um, the identity of the person. Who are they? All right. Is the first thing that's obviously important. So when we talk about identity, we are typically challenging the user to give us something they are. Are. All right. Something only they are. So typically it's something like a username. So we ask them, what is your unique username? It's something that you are. It's part of your identity, like your name, but instead of a name, we often ask for a username. Okay. Why? Because a name can actually be duplicate among multiple people. We could have two Edgar Durons, and then if you say, oh, no, sorry, we can only have one on the system, it'll be a little crazy. So we allow you to keep your name. It may not be unique, but we ask you for a unique username. So something only you are. The next thing we want people to give us that we can use later is a secret. And a secret is something only you know. All right. So something only you are and something only you know are two building blocks of credentials. And the secret we typically ask for is a password. All right. Something only you know. Wait, hold on. Something only you know? Doesn't the system also know your password? Then that's a problem. So we'll talk about that in a moment. But it should be something only you know. Nobody else knows, not even the system. Okay. And the last thing, which we're not going to get into today, we'll talk about it in a different week. Ooh, there's too many S's in here. Possession. Edgar! It's like snake speak. Possession. Give me your possessions. All right. Okay. Something only you have. All right. So typically it has to be some object or entity that only you have access to. A common thing that we ask evidence of is an email address. We assume only you check your email. So it's something only you have is that email. Okay. Another thing that has become very popular over the past 10 years, when we ask for evidence or credentials, is a mobile device, assuming that only you carry your mobile device. Okay. Um, is there any other possessions that are something only you have? Bingo, bango. Yes. Some kind of fob or device that generates a code that only you know, that only you have. Okay. Give me a second. Do not disturb. Okay. Um, so, for example, a lot of banks, when you make an account at a bank, they give you a physical device, and you've got to like punch in a code or something, and it'll give you a PIN number. Like it'll generate a random number. Edgar, you're looking confused. You've never seen this before? Really? Okay. I know somebody who knows. Google. Bank fob. Can I just ask for fob? One of these things. You've seen these things. Like a pager or something like that is what it looks like. Well, it's a device that the bank gives you. Like I have an HSBC account. This is literally the HSBC account. You can even see it here, HSBC. Yeah, absolutely. It's still used. There are other alternative things now, but this is one of the things that is commonly used. You go in, they give you a thing. So when you're logging in, you enter your username and password, and you have to hit a button like toot, toot, that button. It gives you a code, and you have to type in that code as well. So this is an authenticator, yeah, but by itself, it's only something you have. It's not something you are. It's not something necessarily only you know. Certainly not, because the bank, of course, has to verify this number. All right. And it's a random number that is generated according to the time of day or something. So the bank can generate it as well and make sure that it's a valid number. Okay. Some of the devices like this one asks you to punch in a code. Good question, Edgar. Is this something that's actively used today? Is there anything else that is used today? As an app, yeah. Nowadays, a lot of these devices have become apps. So you simply install the app on your phone, and you have to kind of open up the app, and the app will try to authenticate who you are. And then after the app has, and it can do that through your phone's facial recognition. It can do that through a PIN. It can do that through multiple methods. All right. And after the app has verified who you are, then that's the possession. That's the only you have thing. Yeah. Mm. Okay. Yes. 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 So you're right. So again, they're asking you for using mobile or email or something you have. All right. Yeah. So there's multiple ways of doing this, but these three things put together really form today what we call authentication. So when you hear the terms, for example, multi-factor authentication, two-factor authentication, things like that, they're basically saying you need to do all three of these things, bless you. You must do all three of these things to authenticate yourself. A more limited form of authentication is just these two things. Okay. This is bizarrely sometimes called a one-factor authentication, like just the username and password, but it's actually two factors. But what we typically call two-factor authentication, because they're thinking of these two things. All right. But to me, these are all part of your credentials. Multi-factor authentication is at least three of these things, or more of one of these things, one more secret or one more possession or something like this. All right. So this is essentially what authentication comes to. We're not doing authentication today. We're just collecting some of these evidences today. And in particular, I want to focus on this one, the password for today. Okay. And as I'll show you in coming weeks, the password is also kind of sometimes not even used. Oftentimes, people only use this one nowadays. For example, if you want to log into Slack, oftentimes it doesn't even ask you a password, it simply sends you an email and says, just click on that email, you logged in, forget the password. All right. So, two out of these things is necessary, but if you have all three things, it's more secure. All right. Okay. Any questions about it? Yes. Yes. The what number? It could be the same. It could somehow bizarrely be the same for two people. It should not be. But if at the same moment two people try to log in, could they have the same number? They're trying to minimize the probability of that. But as you can see with those codes, they're only 6 digits long, right? So technically, if 1 million people try to log in at the same time, two of them have to necessarily have the same number at least. Okay, but at least they're trying to be as unlikely as possible. Yeah, good point. No, but no, they do not pass you a huge cryptographic key that you have to type in because you will lose all your customers. It will not be compromising you as long as you each have a different identity and a different secret. Okay, great. All right, so that's what our credentials are. Something you are, something you know, something only you have. So in this class, we'll use username, password, and email, but you may use other things later on, okay? All right, cool. And we will talk about authentication in another week, so don't get too excited that we're talking about these things. We're going to just talk about the password, all right? So once we get a password, and so today we're going to talk about collecting evidence. So once you get a password, I want to talk about where do you put it, all right? The answer is the database. But how do you put it in the database? Because one thing we said is the password falls under the rubric of a secret. It should be something only you know, okay? So there's several ways in which passwords can be stored. All of them are terrible. Okay. Um, Obviously, one way that passwords could be stored is just as plain text. Like when the user gives you a password, you could just put it right into the database and save it as a password. All right. Brandon's saying, no, don't do that. Don't do that. Why not? Don't tell me your last security professor told you no. Why not? The database can be compromised. The way I encourage you to think is your database is compromised. That's the safest way to think about it because databases get stolen all the time. All right. Um, all you've got to do is not pay your system administrator one day, and then I always say, like, how much money does it take to break into a system? It's just got to be like, a little bit more than how much you pay your system administrator, your database administrator. That's how much money you need to break into a system, right? Just gotta beat that salary amount a little bit. Okay. Yeah, don't store your passwords in plain text. Everyone knows this because it betrays your user if your data is stolen. Okay. Well, then, no problem. Let's encrypt the password. Let's encrypt it and store it. Right? I mean, we're encrypting everything else, all the other sensitive information. Why not just encrypt the password? It could be decrypted. Well, in that case, I mean, then we can't store any sensitive information, right? This is all encrypted anyway. Like your credit card number is encrypted. Your personal information is encrypted. So why not your password? Oh my God, I almost convinced you guys to encrypt the password. Yes. I mean, like you get the password the first time, you encrypt it with a key, and you store the password in the database. That way, somebody steals the database, assuming you don't store the key in the database, you store the key somewhere else. They can't decrypt it, right? What's the problem? You're all sold. You're like, yeah, fine. Cancel the lecture. We're done. Go home. So the problem is what happens if there is a leak and somebody is able to get your key, somebody is able to decrypt that password. All right. Um, that same problem is for any sensitive information you're storing. However, if you break into a database, you somehow able to, like, you know the key, you have the keys somehow, and you're able to decrypt this, the most you can do is harm the people at this service with the information they've given, right? Like maybe you have photos of them they didn't want to distribute. Maybe you have some personal information or their location or their ID number or their credit card number. You could do some damage to these users in this system relative to this system. The password is a bit more problematic because what do a lot of users do when they're asked to create a new password? Not you guys, of course, right? Birds chirping outside. Shh. um, yeah, a lot of users just use the same password again, right? And if your system is compromised, guess what else is compromised? Their Facebook account is compromised. Their Gmail account is compromised. Their Twitter account is compromised. Heck, their bank account might be compromised. All right, because different services don't talk to each other and say, "Hey, did we get unique passwords?" All right. So passwords are very sensitive in this regard because it should be something only you know, and If you're using it in multiple services, then we have a big problem. All right. I mean, hopefully one day we will resolve a way to make sure that people cannot reuse passwords. But for as long as they can, we cannot simply encrypt passwords, right? Because all systems around the world will be compromised if a password is stolen. All right. So that's why we do not encrypt passwords. And there's one more reason. Puristically speaking, like as a purist, the password falls under something only you know. It can't be something only you know if the system also has your password, right? If the system also knows your password or can derive your password, it cannot be something only you know, all right? So the password, it cannot be just encrypted. It cannot be something the system also knows. This is a problem, all right? So we do not encrypt passwords. So the other option, one other option is just to hash the passwords, all right? Like we have SHA-256, right? Like that's a hashing algorithm. All you have to do is provide it the plain text and it'll provide you a hash. Remember, a hash is something like if you just encrypted the information and then took a small amount of it, like you just took 128 bits out of it, that would be a hash. It's a one-way function. You cannot decrypt from a hash because a hash purposefully loses a lot of information after encrypting it, if you will, if you wish to think of it that way. Okay, so a hash is a lossy encryption basically. So it's a one-way encryption. So a hash kind of matches the bill because if you just hash the password, then the system doesn't know the password, right? That's great. The system cannot know the password. Fantastic. So can we just hash the password? It's in red, so obviously not. So moving on. Why not? Dictionary attack, yeah. Somebody doesn't need to know your password. They just need to have a dictionary and they're going to try all the words. Now, let's be honest. You as an individual are not worth a dictionary attack. No, you are worth it. You are worth everything. But the information in your account is not worth it. All right. No one's going to do a dictionary attack to get into your account. If they use a dictionary attack again is where you just take a dictionary and you take every combination of words and letters and numbers and other things, and you just hash all of them to kind of find out popular hashes. This is assuming someone has stolen the database, right? Someone has stolen the database. They've got the hashed passwords, right? So maybe they want to be able to figure out what is the original password so they can go into through the rail system, okay, through the web system. Um, the downside is, well, what people will do is they will run a dictionary attack, produce hashes of billions of combinations of words, and then use that against the hashes in the database. Okay, and if they can do that, they can get to figure out the password. In fact, if they do that and they figure out the passwords of some users in your system, now we're back to the encryption problem where they'll just go to other systems and retry those passwords, right? They're like with your username and your email account and with your password, they'll just go to Facebook, they'll go to your bank, they'll go to different types of places. All right. So a hash is not good enough because once you've generated a hash, well, anyone can generate a table of hash results and then compare it. So now entering what many people recommend doing, which is salt plus hash. Okay. So when we talk about salt plus hash, yes, when we talk about salt plus hash, we're basically saying get some information, which we call a salt. Actually, salt is just a nonce. Yeah, right. There's a slight distinction between a salt and a nonce, but they're practically the same thing. Okay, it's basically a nonce, and you introduce that to the password, and you hash them together. Now, if somebody runs a dictionary attack on potential passwords, it won't match anything because they don't have your salt. Okay. Well, what if they break into your system and they figure out the salt you're using for users? Well, then all the dictionary all the dictionaries they've developed are useless. They've got to rerun all of them with your salt. First of all, if you have one salt for all the users, then they've got to use that salt and recreate all that dictionary stuff that they had. Is anybody going to do that? How long would that take? Gosh, it would take a long time, right? No, not really. Modern day computers are insanely fast. And people have demonstrated, this is a demonstration from 2012, from a decade ago almost, from 10 years ago. So some researchers said, really? People still think hashing is slow? So they put a 25 GPU cluster together, which isn't a lot, to be quite honest. I mean, I know kids who have more computing power than this because they're mining Bitcoin. So they're like, okay, let's take a break from mining Bitcoin and do something else. Let's take a break. And they applied this 25 GPU cluster to trying to crack passwords by trying to recompute their hashes from scratch. And they found that pretty much every single Windows password can be cracked in less than 6 hours using a computer this powerful. All right. And if you look at a lot of popular hashing algorithms, this is how many hashes they can produce per second. On some weak hashing algorithms like MD5, it's like 180 billion a second. So yeah, they can easily reproduce like salted and hashed passwords if they know your salt. They can easily reproduce this. I don't think, I mean, so no matter how big their dictionary is, I mean, they're going to figure it out. In some cases, in less than a second. All right. SHA-256 is slower. SHA-512 is okay, getting there. It's about 364,000. But still, what is that? Is it going to take them a few minutes to reproduce their entire dictionary attack for your salt? That's a bit of a problem. All right. So, but this is the basic idea of how you would do a salted hash. The code is pretty obvious. I have two passwords. They're exactly the same password. And here's my salted hash function. I produce a salt, and I'm going to use RBNACL. I'm going to use RBNSCL because, you know, I'm a good DJ Bernstein devotee, disciple. So, so I ask RBNSCL, how many, give me some random bytes, and that's my salt. And then I take the password and the salts, I put them together, and I SHA-256 it, okay? That's my salted hash, all right? So SHA-256, SHA-512 gets slower, but not so slow that people will reconsider. They will still use powerful computers to kind of take apart your passwords. But there's another there is another problem, which is if I use the same salts, I am going to produce the same hash for the same password. So there is a little bit of information hackers could get, even if they don't bother to crack your passwords. If they can access your database and they see, hey, these two people have the same hash, assuming the salt is the same, they must have the same password. So that's kind of information hackers can use. So there's several problems with just salting and hashing. The biggest problem is hashing is no longer considered a secure operation because it can be computed so incredibly fast. All right. So nothing is preventing people from doing database attacks on your system. All right. If they have sufficiently powerful machines. And salting is not, you cannot really use the same salt for multiple people for obvious reasons, okay? So what can you do? Well, one easy thing you can do is every user can have an unique salt. That is a little bit more secure, okay? But we still have this problem that powerful computers can actually take apart salted passwords pretty easily now, like trivially now, okay? So this is no longer considered, this is a borderline method of storing passwords today. It's kind of borderline. People have tried to innovate on it a little bit naively. And here's some naive innovations that you will often see in industry. And I say naive because they don't really do a whole lot. They do a little bit, but not a whole lot. They don't solve the underlying problem. Okay. So one is some genius said that if salt is some random numbers, I can create some new random numbers and call it pepper. Ta-da, genius. Right? Give them the genius award for the day. So they said, you know what? We can have two salts. The other is called a pepper. And we'll basically hash this password on the salt, and we'll have a secret salt, which we will call pepper, and we'll store it somewhere else. Okay, that could work. But the problem is the pepper must be secret. And it's kind of going just back to the encrypted solution. It's going back to the encrypt only problem, right? So yeah, the idea of just making something secret is not going to really cut it. We already thought about that with encryption, all right? So I would not say that this may add a little bit of security, but it's not a very hard form of security. It's just assuming they don't find that other secret after they figured out where your database is. Come on, I mean, I think they're going to figure out things pretty quickly here. And some people say, hey, you know what? Just hash the salted password and then encrypt it with a key. Well, yes, but then it has all the problems we talked about before, including if your keys leak, this is broken. All right. So there is a problem with trying to use. Oh, excuse me. Sorry. I'm going to turn the AC back on. Huh? Can someone smarter than me, which is almost all of you, figure out how to use this AC? Why does it say off? Did I turn it off? This guy doesn't have a PhD yet. Come on. If I can't figure it out, I think we need somebody who speaks Chinese, actually, not just somebody taller than me. Okay, just that is the on and off button. Oh crap! I guess we got to open some windows, folks, because it'll be sweltering in here. Okay, this we need Edgar for. 3 Chinese speakers can't figure it out. We're really in trouble. 3 Chinese speakers and a PhD candidate can't figure it out. Yeah. Once in a while, it's suddenly let's go with it. Let's go with it. Something changed, right? Yes, it is feeling cooler now. I think previously we just had the fan on, not the. Yes, I'm feeling something cooler. Are you feeling something cooler? Placebo, maybe. All right. Okay. Um, so all of these solutions have been thought and they've been tried, and they're not like super effective because the problem boils down to this creature, right? This 25 GPU cluster can tear through anything. So the days of just like salting password are unfortunately coming to an end. All right. It's still useful, but maybe by itself it's not enough. So introducing to you what we today consider, for now, the state of the art to store passwords. All right. What we use nowadays is we do not any longer use regular hashing passwords. We don't even use typical cryptographic hashing passwords. Because remember, what are cryptographic hashing algorithms trying to do? They're just trying to maximize entropy, right? And they're trying to do it in the most efficient way possible. Instead, we use a modern breed of hashing algorithms, which are called key stretching algorithms. All right, so they're called key stretching algorithms, and I'll introduce a little bit later why they're called key stretching algorithms. All right, so key stretching algorithms, there's several families of algorithms. So PBKDF is a family of algorithms for key stretching. One venerable one that's been used for some time now, maybe for a decade now, is called Scrypt, and I will recommend to use this in this class. But another one that you can also use is called Argon 2. In fact, Argon 2 was the winner of a major competition to find modern key stretching algorithms. It is as powerful as Scrypt, but is a little bit more future-proof, but it's a little bit younger. So I use Scrypt to this day, but probably in the coming years, I'll switch to Argon 2, but you can switch to Argon 2. It's become quite well regarded, okay? So these are some new algorithms for hashing. What makes them more effective than a regular hash? Here's the funny thing. They're not cryptographically more secure. They don't introduce more entropy. No, that's not the point of these algorithms. The point of these algorithms is to be highly, highly, highly inefficient. they burn a lot of resources to produce a hash. All right. So an scrypt algorithm could produce a fairly good hash after one round, but they deliberately do it for many, 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 many rounds more than they need. And just exclusive or the answer with the previous answer over many, many, many rounds. Okay. What does this do? This produces an algorithm that consumes two things: a lot of CPU power, an unnecessary amount of CPU power, and a whole lot of memory. All right. So it consumes your RAM and it consumes your CPU. Why? Well, first of all, why consume your CPU? What's the advantage in doing that? It's not a better hash result necessarily, but what's the advantage in an algorithm that's so inefficient it burns your CPU? Essentially, it makes it very hard to conduct a dictionary attack. All right. Um, let me show you scrypt in action, so you believe me. Okay. So here's the code. All right. Here's the code for to run scrypt. It's almost the same code to run Argon too. They're both included in the RBNSCL package. Ta-da. All right. So I've made a function called hard hash. This is a hardened hash. You give me a password, I'll produce a very hard hash for this. Okay. Um, the first two things are the operations limit and the memory limit. Like how many operations maximum, how many operations should it be using to compute this hash? So you can tell it, I want you to perform a whole lot of operations, a massive amount of operations to compute this hash. And I want you to use a large amount of memory to compute this hash. Okay. And then this is the size of the hash I want you to produce. I want you to produce like a 64-bit hash. Okay. Um, and how do we use it? Well, RBNSCL has it. So the first thing you need is a salt. Okay. We're still going to use salts, but that's not our only line of defense. Now, when we use the salts, we're going to ask RBNSCL to produce some random bytes, but this time, the number of random bytes that the scrypt algorithm is expecting. All right. So we tell it, please produce random bytes of the size that the scrypt algorithm in RBNSCL is expecting. That constant is with deeply nested, but available within RBNSCL. Within RBNSCL password hash scrypt, you've got a constant called salt bytes. All right. And then to run scrypt, you simply call RBNSCL's password hash.scrypt algorithm. They also have a password hash.argon too. All right. So password hash.scrypt algorithm, and you've got to provide it a few things. Oh crap! I forgot to change the code. Just remove base64.strip decode. You don't need this because this is the raw salt. It should just say salt. This should just say salt. Okay, Edgar. This should just say salt. All right. So what do you need to pass to RBNSCL's password hash scrypt? So notice first of all, it's called password hash. It's not just called hash. This is for hashing passwords. Okay. You pass it the password. You pass it the salt. Then you pass in the operations limit, the memory limit, and the digest size, and it does it for you. Okay. And in my function, what I do is I return the I base 64 encode the digest. Digest just means the hashed data. And the salt, I put the salt together with the digest because in future, if someone wants to verify this password, they will have to rehash the password with the same salts. Okay. Um, okay. So now when I conduct a hard hash on a password, this is my hash. Okay. And this is actually the salt. You see there's a little new line character right here. Okay. So I kind of package them together. I'll show you this is not the final code I will use in my application. I'll show you the final code in a moment. But this gives you an idea of how we can encrypt, how we can, not encrypt, excuse me, do a powerful hash. So now why do I say it's powerful? I say it's powerful because it consumes a lot more CPU and a lot more memory than a regular hash. And let me, in fact, show you how we can do this. run a benchmark test to show you how slow it is. Okay. So I'm going to require ACL base 64. Here's my hard hash function. Okay. My code is right here. It just only uses salt, but I forgot to update the handout. So there's my, oops. There's my hard hash. Okay. So if I was to conduct a hard hash, I forgot to give it password 1, password 2. So if I conduct a hard hash, there is my hard hash. Okay. All of this is the hash of script, and then the new line, and then this is the salt. Okay, cool. Now, let's run a benchmark test. The purpose of script and Argon 2 and these key hashing algorithms is that they're extremely inefficient and hard to compute. And we're going to ask the question why. But first of all, how much longer does it take to conduct a hash using script versus, let's say, SHA-256? Okay, so I'm going to run SHA-256 1,000 times, and I'm going to run script about 2,000 times. You ready? So enter. Oh, require benchmark. Thank God this is not a product launch. It's like your nightmare. Like, no, it crashed. Okay. Enter. Another crash. What the hell's going on? SHA-256 is conducted by. You know what? I should just include this whole damn file. What am I doing? Okay. Okay. Now can we run this? Now I'm not so confident anymore. Yes. Oh, SHA-256 is finished. It did 1,000 hashes in about 8 microseconds. Script is still running to do 1,000 hashes. Anybody want to guess how long it's going to take? 5 minutes? 30 seconds? 2 minutes? 8 minutes? Let's come back to it later. Okay. So, what is the purpose of these password hashes? The purpose is, like I said, to burn your CPU and to completely occupy your memory. Why? First of all, why burn your CPU? Why consume a lot of CPU resources? It's costly and it's slow. Okay? It's slowing down the attacker a lot. How much? You'll see in a minute. So it takes a lot of time, which means if the user wants to create like a rainbow table, like a little dictionary attack table, I mean, just to go through 1,000 words is going to take them, as you can see, a significant amount of time. They're not going to be able to run billions and trillions of combinations and permutations, all right? It's just simply too slow. I mean, they can for one salt, but if they come to my database and they find it's got another salt, it's not worth their time. It's going to just consume a lot of CPU power. Now, I know what you guys are thinking. Your generation's like, CPU, shmeepu, I will use my 25 GPU cluster and I'll kill this thing. Then what? A GPU is going to be a lot faster, and a 25 GPU cluster is going to be a lot faster than your CPU. So have we defeated script? There's one more trick up the sleeve of script, and that is the memory usage. CPUs running on your computer have a lot of memory, gigabytes of memory, right? And they have their limit is their operating capability. GPUs have comparatively much higher operating capability, but relatively speaking, they have much less memory than your main memory of your computer. And GPUs typically don't access the main memory of your computer, otherwise they'd be slow. They have their own onboard memory, which is much smaller. So the memory limit makes it difficult to run this on a GPU or even a GPU cluster. All right, so that's why it consumes both CPU and memory, is to prevent devices that are high compute, low memory, high memory, low compute. Either combination is going to be thwarted this way. Okay, so this is the purpose of a password hash. All right, let's go back and see if script has finished. It finished, and it took about 75 seconds. I ran this last night. It took about 60 seconds, so it's a little bit variable, but it took over a minute to compute 1,000 hashes. All right. Here's some numbers from a long time ago, from nearly 2 decades ago. Holy crap. No, not 2 decades. It was a long time ago, 2009. Actually, weirdly, computing power hasn't increased a whole lot since 2009. But anyway, that's a different issue. But this is the cost in 2009 dollar values and 2009 computing capability. This is the estimated cost of hardware to crack one password, to crack a password within 1 year. Okay, so let's say you said, I've got hardware and I know I've got a password. I don't know like what it is, and I've got to run through a lot of combinations, but I need to crack this password within 1 year. That's the limit of this game. How much hardware power do I need to definitely crack one password, just one password? With the older hashing algorithms, most passwords, 6, 8, 9 characters, it would take you like $1 worth of hardware. It's trivial. All right. I don't even know what $1 worth of hardware is. It's like you rent Amazon Cloud Compute for like 5 seconds. I don't know. Okay. However, when you look at modern key stretching algorithms, for passwords that are at least 8 characters or longer, it starts becoming prohibitively costly. All right. To crack a single password within 1 year would cost hundreds of thousands of US dollars, potentially millions. If you have bigger passwords, we're entering billions in terms of territory. All right. If we increase the memory and operating limits that we require for these algorithms, we can require a hacker to have like more money than the global economy to crack a single password. All right. That's how effective these key stretching algorithms are. They just slow you down and consume so many resources, it becomes financially unprofitable to run these kind of attacks. Okay. Okay. So that's essentially the current state of the art. Yes, we still use assault, but we use assault and we use salt the password and then run a key stretching algorithm on it. Okay, not a regular hashing algorithm. Any questions on this? Yeah. Yes. Is there a what? Than 2009? You don't pay me enough to find a more recent study. I don't know. I would love to find it. The last time I honestly looked was not this year, was 2 years ago, and I didn't find one and I gave up. But if you can Google and find a more recent study, I'd be delighted to know. I don't think it'll change a whole lot. I'll tell you why. First of all, the US dollar hasn't changed that dramatically. And the second of all is computing power, as far as I know, maybe GPUs have gotten far more powerful, but not like 1,000 times more powerful. They haven't really changed in orders of magnitude. We're kind of reaching the limits of what silicon can kind of do, at least on the architectures we have today. All right. Short of having some like quantum compute power, but that cannot be used on all kinds of algorithms, we're kind of at relatively this kind of scale still today. All right. Okay. But that's a really good question, if there's a newer study on this. Any other questions? Oh, I have a question. What is this? Oh, no, we just answered this question. All right. I want to say a little word about key stretching algorithms because they're kind of cool. So the script algorithm, according to Wikipedia, was developed for 2 reasons. It's useful not only for storing digests of passwords, but these password hashing algorithms, these key stretching algorithms, are also used for deriving encryption keys. What does that mean? So this is what we're doing in this class, by the way. Well, let's talk about deriving encryption keys. Sometimes, not always, but sometimes, when a user wants to encrypt a certain bit of information, they may want to provide their own key, right? They may say like, no, I don't want you to give me a key. I want to make a key. Typically, the user wants to use their own key for encrypting an algorithm, for encrypting a document, let's say, when they want to have it a secret in their head so that, like the key is not stored anywhere else. Okay, the key is stored only in their memory, in their mind. All right. And if a user wants to do this, say like on your system, perhaps they say, yes, I want you to encrypt this for me, but you don't make the key because then you'll know the key. I will make the key myself. Please don't store my key anywhere. Now that's a little bit of a problem for us because right now we're storing the key we're using, we're generating the key we're using, right? Why are we doing that? Well, we're generating the key we're using because we want to make sure that the key is complex enough. If a user gives us a key, it's going to be like their dog's birthday or something like that. Like it'll be something completely like short and ridiculous compared to a cryptographic key. All right. But sometimes you just need to give this trust to the user and say, fine, you provide the key. It could be something that even you don't trust yourself to keep the key. All right. So what should you do then? Key stretching algorithms to the rescue. So if the user insists that they will provide a password to encrypt this document, all right, this is not necessarily, this may or may not be the same password they're logging in with, but they have a password they want to use to encrypt a document, okay? What do? Well, their short password is just too short to use as a key. So what you can do is say, thank you for the key. And then the user feels very happy because they generated a key and they feel very smart. Just like you felt when you created your PGP keys and it asked you for a passphrase and you're like, yeah, this is my very long passphrase. It's nothing compared to what a cryptographic key should be. So what did PGP do? It probably did something like this. What your system can do with this ridiculously short password is you can generate a salt, a unique salt just for this user, okay? And you can run their password, their short password, through a key stretching algorithm like Scrypt. All right. Salt plus their short password will give you a cryptographically strong password. All right. So essentially, you thank the user for their measly little password, but what you're doing behind the scenes is you're using their password and some salt to generate a much more powerful password, a much larger password with much greater entropy. Okay. In fact, most of the entropy here comes from the salt. Their password is like, yeah, thank you. All right. Of course, their password helps to make it unique. Well, the salt also does, but all right. And then you use your new stretched password. So this is why it's called key stretching. You're taking a key that someone has given you and you're stretching it into a much bigger and a key with much higher entropy. All right. And you're using that as the actual password in your encryption. All right. And with that, you can encrypt the document and store the salt with it. No problem. Keep the salt. All right. But you should probably have a unique salt for every document you're producing, not the same salt. All right. Because if the user encrypts two documents or two pieces of information with the same password, they're going to end up with the same encrypted document, which also leaks information. So use a different salt for every time you're hashing a document, encrypting a document. Okay. So this is one of the real main reasons for using key stretching algorithms. And this is why they're kind of called key stretching algorithms. All right. Now, I'm not requiring you to do this for your assignment, but you could. It could be a nice little feature to add to your projects if you wish, right? Where there are things that are encrypted, but you do not store the key for the database. The user has to remember their own password. The downside is every time you have to decrypt it, you have to ask them for their password because you need their password to regenerate this digest with the given salt. All right. Okay. For today, we're not going to use password hash. We're not going to use key stretching for that reason. We're going to use it for a different reason. We're going to use it for this. We're going to use it this way. When a user comes and says, I want to create an account, we ask them for their username and password. Later, we'll ask them for other things as well. But for today, we'll just ask them for a username and password. But we don't actually store the password, obviously, in the database. What we do is we generate some random salt, and we use a key stretching algorithm to make their password become a very difficult and an irreversible hash. A very difficult to compute hash that is irreversible. All right. And the salt, we store it as part of the digest. We store the salt we created as part of the digest. So every user has their own unique salt. All right. We don't just reuse one salt for all the users. Okay. And then we store the salted password that has been hashed using a key stretching algorithm. Right? So now their secret is really their secret. We don't know their password. We cannot decrypt their password. And if we tried, it would be computationally infeasible at this point in time to guess their password. Right? So for this class, this is how we're going to use it, is just to basically salt and hash their passwords. However, the same algorithm has this other powerful property that you can generate really nice encryption keys using key stretching algorithms. Right? All right, cool. Any questions on this? You're okay with this? All right. Now, since I'm such a nice teacher, I'll give you all my code that I used in my assignment to do this. It should practically work. Just copy and paste. It should work, unless you want to modify it in some interesting way. Okay. Here's what I kind of here's my code for it. So this week I've created a new model, which is called password. This may be a little surprising. Why is password a model? Many people think of model as like some kind of object that represents database records. It's not. Models are just entities that are useful for your system's logic. All right, so anything can be a model. It just so happens that a lot of the models we're using in this class are SQL models, so they're actually database models. They correspond to database tables. Okay, this model does not. It only corresponds to at most a single field in a database. Okay, so I've made a model called password because I've got some logic that I want to have. And where do you store logic in a system? In model view controller architectures, the logic should always be stored in models. Okay, my SOA class goes into this in tremendous detail. All right, and some students here have traumatic memories, maybe, of that. All right. In fact, the SOA class is all about models, like where does your business logic go? Okay. So I've created a model called password, and what password does is, let's take a look. So here's my password class. It is not a SQL model. It's not correspond to a database table. It extends a module called key stretch that I've written. I've written it right here. In fact, this module called key stretch, notice this is a module, not a class. You cannot make an instance of this. It's just holding functions. Okay. So this module called key stretch is where I have all my RBNACL code is in here. Okay. So this is where I store a function called new salt that generates salt for me. And then I've got a password hash function, which given a salt and a password, will use the correct limits to generate, to hash your password for you. All right. And I use that module within my password class by extending the module. This was a long time ago, but in your tutorials, like your, what was that? Code Academy, thank you. That Code Academy tutorials, when you make a class, you can either include a module or extend a module. When you include a module, all the functions in the module become available to instances of the objects of this class. When you extend a module, all the functions of this module become available as class level methods, not object level methods. All right. So now my password class has several interesting functions. First of all, you initialize it by providing it, if you wish, a salt and a digest of a password. All right. And let's look at the class level methods first. So these, you don't need to instantialize it. If you give me just a password and ask this class to digest it, it will generate a new salt for you and produce a new salted hashed password for you. I mean, it will salt and hash that password for you using a key stretching algorithm. Okay. And then this returns an instance of the password object, which contains the salt and the hash. All right. So interestingly, this is a class level method that generates an instance of this object. Right. Conversely, if you give me something stored in your database and say this is a previously hashed password, then what I do is I unparse that digest. It's going to be stored in JSON in our database, and I extract the salt and I extract the hash, and then I create a new instance of this object. All right. The instances of my object have two methods. One is called toJSON. So basically, it takes the salt and the hashed password, the hash of the salted password, and it just creates a little JSON object out of it. Okay. And then I've got a function called correct, a method called correct. You give me a password, and what I do is I will tell you if it was the right password by reusing the salt to rehash the password. All right. So you'll notice my password class has only logic of how to hash salt and hash passwords and how to check if passwords are correct. The actual cryptographic code is in this module. Right? So having said that, let's go to, can I do a rake? Oh, oops. Let me rake console in today's project. All right, and let me move into credence. By the way, this is why my project is called credence. The cred means we're storing something we believe. All right. So I've got now a password model. Okay, it's called password. So I can say, so what were the, where is our password module? Passwords. Okay. So what can I do with this? So given a password, I can digest a new password like my secret. Okay, and this will generate for me an object of class password, which has a digest and a salt. Right? So I can say this is my pass, or this is my password. Okay. Notice when I'm running password.digest again, you'll notice the digest is completely different than the previous one because the salt is completely different than the previous one. So every time I digest a new password, I'm creating a completely new digest. All right. So pass WD now is my digested password with the salt in it. I can convert this to JSON. And this produces a JSON block with the salt and the hash. Got it? Notice I'm using an alias function. The toS function, which is the function that converts objects into strings, is alias to be the same as my toJSON function. So if somebody takes a password object and adds a string to it, hello. Oh, no, it doesn't work. But let's say they're running some kind of method that implicitly converts this into a string. Okay. Then hello is at the end. It automatically converts this password using the toJSON method. Right. So I've aliased toS to be the same as toJSON. Right. Oh, one example of that, you should not do this, but is if I was to create a string within which password exists. Right. Like my digested password is that'll work, because Ruby will try to convert this into a string now using the toS function, which happens to be alias to my toJSON function. So it produces a JSON out of it. Okay, so that's how I run digest. What else can I do from digest? So pass WD, I can convert it to JSON, right? I showed you that before. Let's say I stored pass JSON. I stored this in a string. So pass JSON is my JSON string. I can now generate a password object from it by using password dot from digest, and here I will give it pass JSON. If I give it a JSON string, it'll create a new password object out of it for me. All right, cool. So now what does this password object have that is so interesting that I keep returning password objects? The password object has two methods that we already talked about, toJSON. The other thing it has is correct dot correct question mark. So here I can give it my guess for the password. I can say foobar, false. All right. Let's make sure that it actually works though. My secret, true. All right. So what it does is basically correct takes the salt, rehashes the password, and checks if the two are the same. All right. And yeah, okay. So that's enough. All right. So that's my code for hashing passwords, for checking passwords. Right. You're welcome to modify this, rewrite this, whatever you want, but you have some working code if you wish already. The next thing I do, and I think this is very important, is remember last week I started saying write some tests that are specific to security. I have some security specific tests here, making sure my password class is actually working. All right, because maybe one day I'll think I'm a genius, I come in, I change the code, and it stops working. So I've got a test here to make sure that I can create password digest safely and that it hides the raw passwords. How do I do it? I just digest the password and I make sure that the string form of the password, which is rather the JSON form of the password, does not contain the original password in it in any shape or form. I've got a test to make sure that I can successfully check a correct password from a stored digest. So I digest a password and then I just check to see that I can check that it's true or false. And also, conversely, I can successfully detect an incorrect password. So it should return false if I try to check an incorrect password, okay? So unit level tests for, and those are in my spec unit folder, right? So this is all I want to say about storing passwords. And I want to kind of introduce you to the state of the art, what I think is the state of the art today in terms of how passwords are stored and why it's different from just simply salting and hashing. Now, I'll tell you, in industry, for many reasons, most people that I talk to are not aware of password key stretching algorithms. They're simply doing salting and hashing, all right? And in particular, they're using what they think are powerful hashing algorithms, such as, I think the most popular one is bcrypt. All right, that's a very popular one you'll see in industry. However, if you talk to cryptographers, they'll tell you that is no longer considered a very strong hashing algorithm because it simply does not consume CPU and memory the way key stretching algorithms can do it. All right. Again, if you go into companies, they'll say, yeah, we're using bcrypt, we're safe. Bcrypt is no longer considered cryptographically safe. It's kind of still effectively safe, but not for very long. Probably in the next 10 years, it'll be unsafe. And then you've got a whole bunch of passwords in bcrypt. So use scrypt or Argon2. Argon2 is considered to be a little bit more future-proof than even scrypt, but scrypt is still pretty damn good. Argon 2 is just very new, so I'm still not using it. Maybe after a couple of years, I'll start using it, okay? So I know what you're thinking now. You're thinking, well, this is all good and fine. But what happens when next year somebody releases a total computational beast of a machine and it's a million times more powerful than, or 1,000 times more powerful than today's computers? What am I going to do then? Move on to a new algorithm? No. Scrypt and Argon 2 are made to be somewhat future-proof. So in future, all you have to do is go into your code and change these limits. Just make them bigger. All right. So if computing speeds get more powerful, which they might, which they will, just make these more powerful. Just make these bigger. You're done. All right. It does mean though that you will have to do a kind of a rotation scheme so that when people log in and they provide a password, you update their hash with the updated limits. Okay. I won't go into how to do that, but I'm sure you can figure it out if you had to. All right. Password hashing. Any questions about this? No? Great. Let's take a little break. It's now 10:19, 10:20, and I'd like to start again at 10:30. So have a little break, get a little refresh.